Hello, everyone, and welcome to our webinar. We're doing again the webinar on our third part of SolidCAM 2017, and we'll be talking today about our five-axis, simultaneous five-axis, HSS, HSR, and HSM, the new features involved over there. And when it comes to talking about these features, there's no one better than Ahmad Onkar to give actually the webinar itself. So I'll be turning over everything to Ahmad in just a moment. Just a quick reminder, when you have questions, write all your questions down in the questions area. And at the end of the webinar, we'll go through the questions and answer them as best as we can. This week webinar is also being recorded and will be available after the webinar. Okay, Ahmad, I will make you the presenter.
Okay, great. All right, welcome everyone, and thank you for joining the webinar. Today we are going to see what is new in SolidCAM 2017 with respect to HSM, HSR, HSS, and simultaneous five-axis. So we now introduced toolpath editing in HSM and HSR toolpaths. They can be edited after calculation, and in most of the times toolpath editing is needed to remove some local areas that you don't want to machine, or to optimize the tool motions, or just remove the tool motions where it's really not needed. For example, in rest roughing, many of the times you would have seen it creates very small motions, unnecessary, at several places, and you had no way to remove those motions. So toolpath editing helps you to remove those unwanted areas, make the toolpath look much better visually. As far as the options goes, we have introduced the three major options that are needed. One is using boundaries, using Z levels, or a combination of both boundaries and Z levels. Okay. So let's move directly into the software, because I believe you would like to see how it works. Okay, so let me open File. Okay, let's go to toolpath editing. So let's open our common HSM file that we do a demo on. And here I'm going to explain to you some features on how the toolpath editing really works. For example, I have the part here, and I would like to remove four corners of this part. So what I'm going to do is I'm going to simply create a sketch. Okay, so I'll click on this, make a sketch. I was also asked, why don't you just give some manual removal of toolpath that would make the making of sketch redundant. Of course, we also have those plans in to give you those options to remove things manually. Okay, let's make four rectangles, and here it is. The next one. Okay, out of the sketch. So I'll right click on my toolpath, and you can see that you have the edit HSM HSR toolpath function. So we are going to use the boundary functions. The tool remains the same. We are not allowing you to change the tool because it doesn't make sense to change the tool. What we are allowing you, apart from defining the boundaries, is your ability to change the linking. Okay, if you find that the linking is not good, you can change the linking. Now this is something very, very important, or it's a standout feature against our editing and the editing that is performed by our competitors, because in the competition only the edited tool portions can be relinked again with a new linking, but all the links that are already existing on the other part of the toolpath cannot be changed. But here you're allowed to even rechange the linking. Okay, so let's pick the boundary. I'm going to create, and I'll say 1, okay, 2, 3, and 4. Now you have two options in this. One is to keep the toolpath inside the boundary, or you want to keep the toolpath outside the boundary. So I would like to keep the toolpath outside the boundary, okay? And I don't want to touch anything on the link. Whatever the linking was there original, it should continue with the link. And we'll hit the calculate button. What it is basically doing is it's going into the passes, trimming off the passes, and performing the relinking again. So you can see that we just chopped out the portions of the toolpath. Now the best part in our toolpath editing is, you don't like this editing? Great. You're going to just delete this toolpath, and you have your original toolpath which is suppressed, and you can unsuppress this toolpath. You get the original toolpath back. Okay? No matter what you have done, you probably would have done something wrong. Don't have to worry. Your original toolpath still is there. As long as it's there, you can redo whatever you did. Now, while we were doing this function in SolidCAM, I realized that you could actually perform the sketch in any plane. For example, I'll go to the side of this, on one of the side, and I will make another sketch here, okay? And I could do the same editing. For example, I'll define the boundaries again, okay? And keep toolpath outside the boundary. Right. Let's look, and you can see that we chopped out the toolpath from this side. So toolpath editing with boundaries will allow you to remove the toolpath from any side, in any plane, in any direction. Okay, as long as you have a sketch, it will remove the toolpath looking perpendicular to that sketch plane. Right, so we have boundaries. What else do we have? Let's delete this. We don't need this. And I'm going to unsuppress this toolpath. And then we have the linear. Okay, so let's look at the linear. Now we would like to edit this linear. And in that, sorry, not just edit, but edit toolpaths with HSM and HSR. I would like to define Z levels. And in the boundary, you can see that now I have the Z levels. So what I will do is, I'll say keep the toolpath from this point and up to this point. Okay. Let's calculate this. Again, it's trimmed off the passes. It's running the links again. Okay, there it is. We've removed between them, and we have kept everything out of it. So we just chop between two Z levels and keep everything else as it is. So this is another example of toolpath editing. You could use a combination of boundaries and Z levels also. You can have a boundary and you can have two Z levels, and it will keep in between that boundary between the two Z levels. So these are the three options that you could use. Now, it's fine on such parts where you have to do a demo, but where is it really applicable in real environment? To see that, I would like to open another part. Okay. I'll open our turbine blade. Okay. And what I have here is, if I edit this toolpath, the original toolpath was with this particular data. Now, what is this particular data part is? Just to stop the tool from going further down, you can see a surface. We created a surface there so that the toolpath doesn't go below that, because I want the toolpath to go this side and a little bit on the other side. But because there's no control on how much the toolpath has to go deep on either side, because once I define my the lowest point in Z, it's going to go on either side. So to stop that, we created a surface. Now what I did was to bring back the old toolpath, assuming that there was no surface there. So I have got the surface removed, so the toolpath is now dropping on either side. But I would like to remove some area of this. So create a sketch. Okay. And then I'd like to make only up to this point. Okay. Sketch is done. Can be anywhere. And we will edit the HSM and HSR toolpath. The boundary, this one. Sorry, and I'll say keep toolpath outside the boundary. Oh, okay. Right, you can see that I created the passes even without having to create a surface out here. So the toolpath editing is pretty powerful. It allows you to do things that perhaps you thought that it was difficult, so you created a lot of geometries to stop it from going into areas that you don't wanted it to go. Let's look at another part. Now this part is pretty interesting because it's from one of my customers, and the problems that you're going to see in the part are typical of when you do a benchmark in die and mold area, or when you do a part in die mold, you'll see this issues typically. So let me open the part again. Okay, this is a slightly complex part and pretty large toolpaths. Okay. It's a forging die, and I've created a lot of toolpaths. For example, I just marked the toolpaths to know that these are the areas. If I open my rest roughing toolpath, okay, you can see that it looks nice, but you see some unwanted motions here, which are actually nuisance value. They are not going to really help you to remove material, but it found some small bit of material, so you have the toolpath here. So what I have now here is a sketch. So I'll switch on the sketches, and I will remove using HSM and HSR. So I have this one and this boundary. Okay, and I'll say keep toolpath outside the boundary. Calculate. Oops. Okay, this is a slight issue. This will be sorted out in the next version, that it keeps calculating the updated stock. Okay, now while we are at the updated stock, I would like to take this opportunity. You can see that in 2017, the updated stock calculation has become much faster. Okay, earlier it used to take a long time to keep updating toolpaths, especially if you had more than 1, 2, 3 toolpaths. The updated toolpath used to take a long time. Whereas now in 2017, a lot of changes have happened inside the updated stock manager, and you can see a lot of things being removed and made extremely fast. The updated stock is now much faster. So those areas are gone. Okay, that could have easily added another couple of minutes to my machining time, and I've removed them. Okay, so one of this is that, and the next one is a slightly more complex toolpath editing, because this is generally what is seen in finishing. The slope angle itself has a limitation. It's a process kind of a limitation, and you can see that it's machining this fillet, it's machining small portion of the fillet here. Okay, it's doing a lot of unnecessary things that I don't want it to do. For example, it's also doing this one halfway here. That's because of the slope angle. Okay, these things, especially in linear machining, can add quite a lot of time into your machining time. It can eat away your machining time. Okay, so here again the toolpath editing comes into picture. Already I have created a sketch for me here, so I'm going to edit with the boundary, and here I would like to pick this boundary. Okay, two boundaries out here, and I would like to keep the toolpath outside the boundary. Let's calculate. Okay, that's done. You can see that the toolpath now looks much better. We chopped off all those unwanted areas, which could have easily eaten up at least about 10 to 12% of my machining time. I've saved machining time. I've saved the unwanted movements of tool, rubbing into certain areas, doing nothing. Okay, and because these motions were pretty small, the amount of time that it takes to machine those areas dramatically increases because of the acceleration and deceleration patterns of the machine. So, moral of the story here is toolpath editing is it's a pretty important feature, both in terms of optimizing the toolpath and also creating a perception in the mind of the customer that we have everything what it takes to machine a die and mold part, a complex part. If you want to edit a toolpath, you want to chop out certain areas, you can do it. You can do it in any plane, any way you would like to. Right. So we had toolpath editing with boundaries, toolpath editing with Z levels, toolpath editing in any plane. I showed you a plane with an XZ plane, okay, and also the toolpath editing using a combination of Z levels and boundaries. While we are in the editing functionality itself, I would like to show another nice feature, and that is to have a gauge check of features in HSM and HSR, especially if you're using clamps and you would like the software to take into account the clamps that are there, which are not part of the target, but they are part of your fixture that you have defined in the setup. Okay, so let's open another part. Oops. Let's open into part editing. Okay, the fixture gauge check. I'm going to open a part here. Okay. So you have the part in front of us, and what you also have here is a toolpath. Okay, I have a complete toolpath, but then I realized that I would like to put clamps onto this part, and I want the toolpath to take into account the clamps that I've put. Okay, for example, I have clamp set 1 here and the set 2 here. So I have 2 clamps that I've put, and I would like to take into account these 2 clamps. Now, you would ask me, Amod, we already have toolpath editing. Why are you showing us a feature that requires another kind of trimming of the toolpath? The difference between toolpath editing and checking with fixture is that in toolpath editing, you're just removing a portion of the toolpath straight down. Whereas in fixture checking, what it basically does is it checks also your holder against the fixture, and it trims the toolpath in such a way that it takes care of your holder also, and it also takes care of those bolts and things coming out so that it doesn't collide when it's doing relinking. So let's edit this toolpath, and if I go into the passes, in edit passes, you have got an option of gauge checking while linking. The gauge checking while linking takes into account your clamping fixture, which you have defined in your setup. Okay, so you don't have to redefine them again and again. But in any case, you would like to define a different fixture than what has been defined in your setup, you can always do that. Okay, right. Let's save and calculate this. This will take about 15 seconds.
Ahmad, I also understand that this also helps. This gives you the opportunity of not having to create a boundary. This way, it just takes it automatically.
Yes, you don't need to create a boundary. It takes into account automatically. And the best part is we'll see that when you're trying to do the simulation. So let's simulate this. Solid verify. Okay, you can see the clamps in place, and we will run it. But you have to make sure that your next toolpath also has to have the same clamps. If you forget it, you're going to have collisions. But anyway, you can catch those collisions in Solid Verify. You can see what it is doing out here. It's leaving the material because it's detected that the holder is coming pretty close to the fixture. So it's going to remove or it's going to have a collision. So it's keeping on, it's keeping the material out here. Okay, so this is how the fixture collision works. Fixture collision works in every toolpath. It works in the roughing as well as the finishing portions of HSM. Right. Let's move further. Of course, this is a small functionality, but it's pretty important. It's the customization of your toolbar. It's pretty simple. For example, in 3D, I can go out here and I can ask for customize the command manager. And if I go into the commands or the menus, sorry, where is it? It should be here, HSM. Okay, you've got all these buttons. Okay, each button corresponds to some or other toolpath. For example, my customer or even you use constant Z a lot. Why do you want to go to add toolpath HSM and in that you want to select constant Z? Better than that, I'll just drag this and drop out here, constant Z, which is the other area that I use a lot. Maybe I use the combined constant Z with linear machining, so I can pull it out. And maybe I use the maybe the 3D constant step over, so I can bring it out. So you can bring out whatever functions you use extensively, and then a click on that will directly open the constant Z machining or whichever function you have dropped on your toolbar. Okay, so it's a nice way to reduce time. Otherwise, you would have done 3 or 4 steps. We just do this in one click. Okay, great. Right, we also come to the next area, and that is a very small function, that a very small button, you can say, introduced to detect flat areas in roughing and in constant Z machining. Okay, with this option enabled, each step down is automatically adjusted to machine the flat areas, especially when you have the flat area coming in between two Z levels, and you will see that a lot of material sometimes gets left out on absolute flat areas. Let's open a part. Okay, let's go up. Okay, flat areas. Simple part, but it explains everything what you would like to know in the function. Okay, so let me edit this toolpath, and you can see that in the passes you have got the detect flat areas button. I'll not switch it on, and I'll just calculate this. Few seconds to calculate. Okay, and if I go into my front view, you'll see that, for example, this flat area came in between these two Z depths. A lot of material is being left out here, a lot of material left out here, a lot of material left out here. What we will do now is to edit, and I'll select the detect flat areas function and calculate. You can see that it introduces one more down step just to remove those flat areas, so that you can get uniform material remaining on these steps or flat areas. Small function, but pretty important one, especially considering the fact that when you have large parts and when you want to do roughing, and they have a lot of flat areas, you would like to see that material remaining is uniform for the next operation, then this button is pretty significant. Okay, let's move now to the simultaneous 5-axis and HSS area, where again a lot of changes have been done. Okay, and in fact, as we progress into our versions this year, you will see a lot of new functionalities coming inside 5-axis and HSS. Okay, so the first function here is a nice function called exact step over. Let me open up part and I'll show you what was the problem and how it has been fixed. Okay, let's go to the exact step over. Okay, here we are. This is the part, and I have created an HSS toolpath with a step over of 1 millimeter. Okay, so if I show you the toolpath, you will realize that this has been a common problem for us for years. Okay, large step overs and then again reducing to get the final step over. The problem here is we used these two curves as our morph curves. So what HSS does is basically it internally creates a surface between those two curves and then unflattens the outside area to project these cuts that are there on this small surface. It starts projecting on these surfaces, the drive surfaces, basically 1, 2, and 3. It then realizes that the width of the surface is much smaller than the combined width of all these 3 surfaces. So it tries to distribute the same number of passes on these 3 surfaces. What happens, the end result? The end result is that you get ununiform step over. Sometimes it's really very large. If you're given a depth of cut of 1 millimeter, it can sometimes end up to 5, 6 millimeters in some areas, depending on the steepness of the area and also the width of the surface. So what is the new function? The new function is a very small function here. In the step over calculation method, you select the exact. What this basically does is it brings in a new algorithm in the back end, and it helps the software to calculate step over on the surface and not to calculate it on the morphed surface and then distribute it over the drive surface. So it calculates it exactly on the surface. So let me hit the calculate button. Yes, please. It's done, and you can see what happens now. Using the exact step over, the step over distribution now becomes very nice over multiple surfaces, especially when the surface that has been created by those 2 morphing curves is small and the net result of the other drive surfaces is a pretty large surface. Very important function. I remember in one of the parts, unfortunately I cannot show you because it's a confidential part of the customer. We had to actually change our complete method of machining just because we were getting ununiform step over. Sometimes we machine one surface, then we machine the next surface, then we machine the third surface. We machine them separately. But when you want to combine them together and do it, if you did not have the exact step over function, then it was really very difficult to achieve constant step over on those surfaces. We really struggled with that part on the customer, and when I finally asked for help, they had this function. They just switched it on, and the toolpath was very nice. All right, let's go further. Another new function inside simultaneous 5-axis. I would not say HSS because it's not in HSS, it's simultaneous 5-axis, and that is called as a common direction detection. What is a common direction? Let me open a part to understand what it really means. Okay. So let's go to the common direction. Okay, so we have a part here, and I would like to machine this surface. in 5-axis. Why 5-axis? Because I have got two surfaces here which are having a negative angle. So I want the tool to tilt as it approaches the surface here, and I also want the tool to tilt as it approaches the further surface here. And then I have a combination, which is a fillet, which has got both this angle as well as this angle. So the tool path here looks something like this. If I just run the simulation, okay, because I have defined the tilt starting from a point, because I don't want the tool, I don't want to create a gouge check situation where within a short span of travel it tries to tilt. So I want it to tilt uniformly. So I've tilted it through a point. Okay. So what it basically does is, as it approaches that surface, because I've used a point, it's going to tilt itself and go into this area here. Okay. Now, what common direction does? Common direction takes into account the check surfaces that you have defined. Okay. And then it tries to find one 3+2 position, a perfect 3+2 position, which when applied will remove all the 5-axis motions. It will just tilt the tool to that particular A and B, B and C, or A and C angle, lock itself, and do every machining in 3-axis. Okay. So what do you have in common direction here? So if I go into the tool axis control, you have got a common direction, or maintain common direction. Now you can ask to maintain the common direction on the entire tool path, or only on single contours where it's actually going to affect the tilting. But it always makes sense to have the entire tool path tilted and machined in simple 3-axis than to just machine some portion in 5-axis and some portion tilted in 3-axis. Okay. So if I switch this on, the maintain common direction, SolidCAM will find a common point or common axis through which it will apply the tool path. So it will create some kind of a 3+2 position, okay, and it will machine the entire surface not in 5-axis but in 3-axis, because it's already positioned itself in such a way that it is going to avoid tilting, to avoid gouges onto these 3 surfaces. So if I now look at the simulation of this tool path, okay, you can see that this is the common direction that it found. It says this is my best possible direction to machine these surface having these 2 gouge check areas. Okay, so it will maintain this direction all throughout the machining. Simple 3-axis. Now you can imagine what would happen if you're going into a pocket which has got a couple of negative areas and you would like to machine the floor. A very nice solution. Just switch on the common direction, select the gouge check areas, and SolidCAM will find you the best possible solution to machine those areas. You can see that it's positioned itself in 3+2, and it's doing the remaining areas in simple 3-axis. A common direction, very important function. It was due from a long time. We introduced it. You can use it on paths. You have understood now the theory behind common direction. You can now think of examples where you would like to use this function. Okay. Let's move on. And we move on to one of the most important things that we introduced in 2017. And that is the support of new tools. The nomenclature here when we created the presentation was wrong. It's basically a barrel tool and a oval form tool. Okay, so we have introduced the 2 tools here. And why we introduced it? Because these tools are getting very popular. And if you know this company, okay, Emug Franken, which is basically a German company, and they're pioneered in this cutters. I was at EMO, and we had our booth, and there was another booth right opposite to our booth of Hypermill, and they were pushing this tool very hard. Well, we were saying iMachining saves 70% of the time. They put a huge board saying the barrel tools save 90% of the time, and they're right. Okay, I'm going to show you an example on how it really works. Okay, so currently we are supporting this tool, the one that you're seeing on the screen, which is the oval form. But in our version that is going to follow after this, we will introduce another tool, and that is the one with taper form. Both the taper form as well as what we would call the lens type tool, okay, for machining flat areas or floor areas. So right now let's focus ourselves on the oval form tool. Okay, first of all, we need to understand why the oval form tool, or why this shape has come into existence. Okay, let's open a part. It's much more easier and simpler to explain why this tool has been conceptualized, or why the shape has been conceptualized. Let's open. Okay, so I want to machine this turbine blade on a 5-axis. Okay, now because it's not straight, okay, I would like to use a tool. There are different options now for me to use. Number one, I could use a bullnose end mill. Let's say a 20 bullnose with an R3 corner radius or R5 corner radius. Or I could use a ballnose tool, a diameter 16 or diameter 20 ballnose tool. Or I could use the oval form tool. Now, what is the difference? To understand the difference, I've created a sketch. Okay, let's switch on the sketch, and let's go to the top view, and let's edit the sketch. So this is diameter 16. That's the ballnose tool. When a diameter 16 rolls over a flat line, I've just created a line to show the contact. To achieve a scallop of approximately 5 microns, 4 to 5 microns, to achieve that scallop, okay? 4 to 5 microns generally is considered to be a pretty good finish on such parts. To achieve a scallop of 4 to 5 microns, I need a step over of about 0.5 millimeters, okay? So I need to define the depth of cut of 0.5 millimeters. So what do I have here? If I come out of the sketch, I have the tool path, which I have created using a regular ball nose cutter, and it has got 0.5 millimeter depth of cut all the way down. Okay, and if I check the time, if I run the simulation, sorry, not this. If I run the simulation with the time, okay, I generate a time of 32 millimeters. Oh, sorry, 32 minutes. I'm sorry. What I did then was to take the Imug Franken tool, and I used a 16 millimeter oval form tool, which has got basically two radiuses, R1, the tip radius, and the flank radius. The flank radius is 75. That is what is going to be in contact with our surface for machining. So I have got an R75. You can say I'm using a ball nose of R75 or 150 diameter ball nose I'm using to machine that particular area. Okay, so if I jump back onto my sketch again to figure out what is happening with the scallop. Okay, let me edit. Now, if I want to use the same scallop, okay, I will generate what I've done here is I have increased or given a scale of 10. Otherwise, it's very difficult to figure out this point. So this is currently 5 microns. Okay, it's about 0.045, 4.5 microns. To achieve that same scallop, so it's going to be 15 divided by 10 because I've done it 10 times. It's 1.5. So to achieve the same scallop of 0.045 with the oval form tool, I need to take a depth of cut of 1.5 millimeters, which is 3 times the depth of cut that I would take with, or rather it's 1/3 of what I would take with a ball nose tool. Okay, so I have got this tool path here, which is with the oval form tool, and you can see that when I run the simulation, let's go here. So I have the oval form tool with R75 as my flank radius. Just take it down so that you can see the contact. Okay, let's stop it. We'll take it out to the main area. Okay, I'm going to switch off the tool path. So you can look, our flank is in constant contact with the surface. So we are using R75 to calculate the scallop. So R75, when I use at 1.5 millimeters, I get the same scallop that I would get by using 16 diameter ball nose at a depth of cut of 0.5 millimeters. What is the time? So if I run the, or I don't have to do that, I'll just go to CAM tree view and I'll switch on the machining time. What you can see here, almost 33 minutes down to 6.5 minutes because of our step. So how much is that? So let's see what Hypermill was saying. Can we achieve that in SolidCAM? Sorry. So we have 6.5 divided by 33. That's almost 19. So we're talking about 81% savings in cycle time. Okay, no longer 70%. We are talking 81% now in 5-axis using the oval form tool. Now, there are certain things that you need to take into account when you're machining with an oval form tool. First of all, with an oval form tool, the tilt has to be defined by the user. Okay, whereas the next tool, the taper, what we call as a taper form tool, what we have here, the taper form tool, form A, the alpha by 2 or the tilt is given by the tool manufacturer themselves. Okay, so this is when you're using the taper form tool. But for oval form tool, you have to use the tilt angle by yourself. Another very important aspect, these are finishing tools. You cannot use them for roughing. These are exclusively meant for finishing, and the maximum allowance that you can use is between 0.2 and 0.3 millimeter. You cannot go beyond that. They are not meant, as per Franken, they are not meant to remove much higher amount of material on the flank side. Okay, so you need to keep these things into mind when you're using the oval form tool, not to give it more than 0.2 to 0.3 allowance to remove material. And the most important, the tilt. What I've done here is I have used a tilt of 80 degrees, so about 10 degrees away from the surface I've used to get the flank to cut the entire surface. Very important addition to our portfolio in 2017, the circle end mills. Okay. In simultaneous 5-axis, we have now have the possibility to use flat end mills and bullnose tools in roughing multi-blade parts. Okay, it was just ball nose and taper ball nose earlier. We have removed that limitation. You now can use flattened mills and bullnose tools to do machining in multi-blade for roughing. For finishing, we have added the support of lollipop cutters in multi-blade. Okay, so we have got some new tools coming in multi-blade machining, both for roughing and finishing. Port machining can now be performed as a 4-axis operation. Earlier, it was only restricted to 5-axis. Now you could machine ports or tubes on simple 4-axis machining by taking the output in 4-axis. Right, now before I jump into the next operation of multi-axis roughing, let's go to a very important addition to our 5-axis portfolio, and that is a new operation called screw machining. It was inside SolidCAM from a long time, and we were doing a lot of tests. We were waiting for it to stabilize, and a lot of things have now come up, and we finally opened it in 2017. Screw machining is, you could say, just like multi-blade machining. It's meant for specific family of parts. Extruder screws, screws that are used in oil and gas, for pushing liquids, propulsion screws, a lot of these parts. So it is used to machine a lot of families of parts. It's as simple as multi-blade. Even I think it's even more simpler than multi-blade, where you just define the part, the axis of rotation, the tool, the depth of cut and sidestep, and the rest is done by the software. Okay, so the user just has to select the part. He has to say, okay, I have my stock, this is my tool, this is my depth of cut, and this is my sidestep. It does everything automatically. So let's open a part, and I'll then tell you another story. Let's open screw machining. Let's open a simple part, because then I can tell you the context of the story. Okay, I have calculated this because screw machining takes some time to come up with the tool paths for roughing and finishing. So that's the reason I don't want to do it in front of you, so I've already done the calculation. So what do I have here? If I edit this, in screw machining, I have the geometry. Geometry, when I say machining surface, you can pick directly from the target here, or you could define it by yourself. Okay, you then define whether you want to do roughing or you would like to do finishing. If you want to do roughing, what is the offset that you would like to keep? And then you have got the machining areas. The machining areas here cannot be defined as a boundary because it's a cylindrical part, and there's no way to define a boundary on a cylinder which encompasses everything. So the machining area here is defined into, or split into, 2 areas. One is the axial limits. That means, do I want to machine the entire length of the screw, or do I want to machine only a portion of the screw? So that's what I need to define. I need to define, this is being my 0, I need to define the minimum point and the maximum point. 2 points, and it will machine between those 2 points. And then I have got the angular limits. Because it's a cylinder, 0 to 360, I can specify that I want the screw to be machined only between 0 and 90 degrees and not to be machined anywhere else. Okay, so I can define the areas in 2 ways. Then simple tool. In tool, we support bullnose and flattened mill. Okay, levels, you can see most of the areas are automatic. The only thing that you need to define here is the entry safety distance and the exit safety distance. In toolpath parameters, you need to define the cut tolerance. Now, when we were doing the testing, a lot of my people did a mistake of defining a very close tolerance. You have to remember how it works. It creates an imaginary cylinder, which is encompassing the entire part, and slices the cylinder along with the part. Okay, cylindrical slices. If you're going to keep your tolerance very tight, it's the STL data that is going to be created is going to be huge, and it will take a lot of time to perform the slicing. Since it's roughing, you don't have to keep a very close tolerance. You could keep it at 0.1, good enough. You define what is your depth of cut, you define your step over. In the tool axis control, all you need to define is the fourth axis. Which is your fourth axis? Is it x-axis, y-axis, or z-axis? Okay. And in the link, you need to define where to use the ramp and where not to use the ramp. Okay, so that it becomes easier for it to apply. Once that is done, it takes, for example, this part. If I measure this, okay, if I measure this part, this is about 400 millimeter. A 400 millimeter screw with a diameter, if I'm not wrong, showing me that. Let's switch on the cylinder because that will be much more easier. So, a diameter of 120, a length of 400, and a diameter of 120. This part, the roughing, is performed in about 15 minutes. It generates the roughing toolpath in 15 minutes. I told you that I'm going to tell you a story. When we were running these tests, there were quite a handful of people who said, oh, this is very slow. When we say it is slow, we have to compare it against something. Today, we do not have anything to compare it with. So the question of it being slow or fast actually does not arise. Okay? I will show you another part which will clear the air about what is slow and what is fast. Okay? So 15 minutes to calculate roughing. It's like simple 3-axis. There's nothing complicated in the definition. You just say, I want to machine from here to here. This is my model. This is my tool. This is my depth of cut, my side step. Calculate. Calculation is done. We also allow you to perform finishing of this part. Now, this finishing took about 12 minutes to calculate. Okay? No big deal. But this particular tool path is ready to go onto the machine on the very first attempt. No need to tweak it. No need to see, whether we are getting the right angle or not. This tool path is meant for this part, and it will go onto the machine on the very first attempt. So this part, from roughing and finishing, these two tool paths took approximately, let's say, 30 minutes to calculate. Now, if I give this part to any of my users and ask them, please use our generic 5-axis engine and create a tool path for roughing and finishing, I'm sure it's going to take a couple of hours at least before they get the tool path out to even check it. Okay? Now, this is a very simple part. Let's look at another part. Now, this is something that's coming straight from the shop floor. Okay. We have this part, 1.8 meters long. It's not a simple screw. You can see what is happening here. You have cutouts. You have got cutouts here. It's stopping somewhere here. So it's not complex. So if I now throw this part, or if I give this part to my user and say, please use our generic 5-axis engine and calculate the tool path. Number one, they're going to say, look, it's going to take me a couple of days at least to calculate. Of course, because you need to do a lot of geometry modifications. You need to close certain areas, machine them separately. And honestly, roughing out this part is not going to be an easy job at all. You need to do several iterations before you come to the exact point, or where you're going to get a tool path that's comparable to what the screw machining is going to give you. So the roughing with 25 R5 took 22 minutes to calculate, and it is done every area perfectly. Okay, the same one finishing took about 30 minutes to calculate. Okay, now you're seeing a lot of retracts because it's treating regions separately. Okay, it's treating the regions separately. It's machining, for example, even if I go to the end, it's done a pretty neat job out here. Okay, this is something that's really unimaginable in our generic 5-axis. If I have to try this in any way to machine in our generic 5-axis, it's going to be a nightmare for the user. So let's say half an hour for finishing and half an hour for roughing. 1 hour against the face of a programmer when he looks at this part and say, I have to do this. God, I have to do this on a generic 5-axis. It's going to take me at least a day to figure out what to do. We are not slow. We are fast. We are very fast because the preparation time is nothing. You all need to define your stock. You need to define your part. You need to define your start and end points because you would like to control how much machining you would like to do. You can also do a partial machining, or you could do the entire machining. And define your tool, your depth of cut, and calculate. That's all is needed in this. You don't need to define the tool axis control. You don't need to define the couch checks. You don't need to readjust the step over to see, oh, this is not going into this area, so let me reduce the step over. All those things are past. With the new screw machining module, you can actually do your job much faster, much quicker, and with very less effort. I want everyone to run this on their parts. I'm sure you'll be having this part. According to our survey, we have got at least 50 times more customers who are doing such parts than multi-blade customers. So it's like 50 times much bigger market than multi-blade. So I want you to evaluate this. Come with us with some. If you have discovered some issues with the software, please let us know. Okay. Right. We now jump into the last part of my presentation. I'll open a part now, and this is for multi-axis roughing. And what we have in multi-axis roughing is stock definition by surfaces. Many a times I have had to deal with parts that was machined somewhere else, and we had to do certain small areas only in multi-axis roughing, and the software used to create toolpaths everywhere. That's because it still recognizes that there's a stock remaining on the other portion of the part. Now with a new option, you can now define local stocks. That means you can close that area and say, okay, I have this area here, which is my stock. For example, the part here, I don't have to define the updated stock. I'll simply go into my toolpath, and in my toolpath parameters, I've got the stock, and you have a new option out here called surfaces, stock by surfaces. So what I've done is I have defined the outer surface, and I've closed a top surface here. So let me open the top surface. Okay. And if I click on show, I've selected all these surfaces as my stock. I don't have to depend on it to do a calculation again with the updated stock, and then there would be some small scallop remaining, and it will go to machine that. So once you have defined a local stock, what it does basically is it generates the toolpath straight away inside. It doesn't go anywhere out. It just machines what is there inside, because it knows that the outer area is finished when it compares it with the target. It knows that those areas are finished. It need not touch them, and it knows that these are the only areas where the stock is remaining. So stock now can be defined using surface, or it could be defined by just a 2D boundary. Okay, not a 3D boundary, but a 2D boundary. You can use a 2D boundary and isolate and tell to multi-axis roughing that this is the area that you have to machine. This is my stock, and it will only machine those areas. Right, so we have come to an end. We've almost taken an hour, slightly more than an hour, and we have come to the end of our what's new in 2017 for SolidCAM HSM, HSR, HSS simultaneous 5-axis functions. Remember that we are adding more and more functionalities in our version, and as it progresses, you are going to see a host new of functions that are being added into SolidCAM's basket of milling. Sydney, I'm done. If there are questions, please let me know.
Okay, Amol, first of all, thank you very much. It was an extremely informative webinar. There's a lot, I'm sure, of information that went out there, and it's good to see all these new improvements. We have one question for you. They'd like to know that if they can select a 3D boundary while using HSR and HSM toolpath for editing.
Yes. When you use if you want to use a 3D boundary, then it's restricted only to 3D toolpaths. You can't use a 3D boundary to edit a roughing toolpath. Okay, that is ruled out. You can use 3D boundaries to edit any of the finishing toolpaths. Now, these 3D boundaries, you could construct it by yourself, or you could simply go into the constraint boundary definition, and you could use any of these functionalities to generate the 3D boundary and edit the toolpath. Okay, but remember, you cannot edit a roughing toolpath, HSR toolpath, using a 3D boundary. It will not take into account. It will just project it onto a plane. It will make it a 2D boundary and then edit it. Okay, the result will not be what you would like. You can use 3D boundaries only for finishing toolpaths.
Okay. First of all, again, thank you very much. I just want to remind everyone that the webinar has been recorded, and it will be available on our website. I'll show you exactly where on the website. Just a moment.
Sydney, I have to show something else.
Okay.
Can you make me presenter? Because there's a question from Shimshon.
Okay. Oh, I'm sorry. Oh, I see it just popped up. Okay. All right. You can go ahead. Go ahead and ask the question.
No, I know the question, what he wants to ask. I want to show it.
Okay. So I'll make you a presenter again. Just a moment.
Yeah.
And okay, there was a question. Okay, now I see the question as well. There's a barrel-shaped and move touch point handling. How does that work?
Shimshon, I have not exactly checked the move touch point handling, but I would like to show you this functionality, but I have not checked it. Okay. I was doing a training in Italy, and one of their customers, very experienced customer, asked me that if I have to machine this surface, okay, and I'm using an end mill, okay, Shimshon, I'm coming to your question, but I've not checked it with the barrel, but I've checked it with an end mill and ball nose. It works perfect. They told me that when I have an end mill, I have a cutting length of 40 millimeters, but I do not want the same point to cut on the surface every time. I want to keep shifting my contact point up, so that I use the entire flute of the tool. It's possible. So let's see how it is done. I'm going to select an end mill because it's going to be much easier to show Shimshon. I'm going to use 16. Let's say that 55. Cut length is 45. Oops, that's okay. So my cutting length is 45, and let's make it 90. Let's switch off the cut check. We don't need it. 2 part parameters, step down 5. Zigzag. Okay, let's calculate. Okay, this is done. Now, what I will do here is small change. I'll create an offset of the surface so that it's much more easier for us to see the result. Make it 0, and I will switch off the solid body. Okay, so I have this. So what basically the customer wanted was, like, if I do the simulation now, you can see that if I go to the side, you can see that the same point on the tool is always in contact. You can see it now. The same point is in contact. Okay. The same point is in contact as it goes down. So what you actually going to happen to the tool is, this portion of the tool is actually going to wear out much faster than the other areas of the flute eye machining principle. So he asked whether, the customer asked whether we could shift the contact point while we were doing the cutting. It's possible. Of course, I did not have the answer at that time. There is a function here called as axial shift. Okay. So we use our axial shift and we move from 0 to, I'm not very sure, it's plus 45. Okay, because my cut length is 45, so I'm going to move from 0 to plus 45. I think it's minus 45. Calculate. Oops. Let's define this again. Okay. Start edge is this. No. Okay, this one. And my bottom edge, tangent propagation, is this one. Okay. And let's calculate. Okay. Oops. Some issue with the link. So zigzag link. Okay. Okay. So let's see what happens now if I move to the side. What happens to the tool? If I simulate this, that's my first point, and you can see that it started shifting the contact point. Now the contact point has gone up. As it starts moving up, it's changing its contact point. It's not keeping the same contact point. Okay, it's no longer this. It's come somewhere here. So what it is actually doing is, it's distributing the 45 millimeter cut length. It's distributing this 45 millimeter cut length over the entire surface, so that the same point that cut on the top is not cutting the next pass. The next pass, it is shifted up by some amount so that it distributes that 45 millimeters over the entire surface. Shimshan, I will try it with a barrel tool, but not here or online, but I will try it with a barrel tool and I'll let you know if it really does. I think it should still do the same thing because the functionality is the same. Okay?
Excellent. Thank you very much again for the answers as well. Just a reminder that the webinar will be, as I mentioned before, available in the reseller section of our website. Okay, take care, everyone. Have a great weekend. I hope you all enjoyed the webinar.